The need to explore is written in the DNA of every person who's ever lived. In virtually every age and place where humans have left records, there is evidence of exploration.
From our earliest ancestors right on through to today, the desire to learn and challenge the human mind has been a cornerstone in our development. Hi, I'm Jennifer Pulley.
And I'm Johnny Alonzo, and today on NASA 360, we're going to take a look at why humans explore and how we're doing it in today's modern age.
History is flooded with stories of humans reaching beyond the known into the unknown to help advance their societies. Now, when you look back, a clear pattern emerges. After attending to their basic needs of survival, virtually all societies turn towards questions of philosophy, like, why are we here and where are we headed?
In our early history, the answer to these questions were communicated through folklore, passed down around campfires or written in ancient texts. Practically every society had stories of gods and mythical creatures that were used to explain the mysteries of the heavens and of human existence. Of course, today, our understanding of science and our use of modern tools like telescopes and spacecraft have helped us replace those ancient stories with scientific facts. The knowledge we have garnered by using these modern tools has helped us better understand not only our own Earth, but other planetary bodies around the universe too. All this knowledge has truly changed how we think of the universe and our place in it.
But even with the wealth of information we have learned from our numerous space missions, there is one major question that still needs to be answered. Does life exist anywhere other than Earth?
In recent years, NASA has sent missions around our solar system in an attempt to find that answer. Although the anecdotal evidence is strong that it does, there is still a need to look further and use smarter techniques to help us validate our findings. For that reason, future missions are being planned that will use state-of-the-art technology and robotic precursors to help answer some lingering mysteries, while also scouting the way for eventual human missions to come. To help me better understand what we are learning about our universe and where it may take us in the future, I spoke with NASA's Director of Planetary Science, Dr. Jim Green.
Jim, let's start off with an easy question. Why do you think humans have a need to explore?
Well, when you look back in history, the kind of answer is all about, well, we just need to explore, we need to see what's on the other side of the hill. Columbus, Magellan, you name it, Lewis and Clark. But for me, it's far different. In reality, it's all about discovering something that is so exciting that no other human on this planet has found out about before. It's all about discovery. Humans are going to leave low Earth orbit. It's in our nature, as we talked about earlier, to explore. So where are we going to go, and what do we need to know before we go there? This whole field is not like Star Trek. It's not go where no man has gone before. Before we send humans anywhere, we're going to want to know everything about the environment that we can. And to do that, we need robotic instruments, robotic spacecraft. We need to be able to rove and understand, take samples, and determine whether those environments are safe or not, or how to survive in an alien world.
Okay, Jim, here comes the loaded question. Do you think there is life outside of our solar system?
The scientific facts seem to stack up in a positive direction concerning life may have existed outside the planet Earth. Now that is a really exciting proposition. And in terms of where we would go, we know now enough about the solar system to recognize there are several key objects that we need to investigate further to determine if life perhaps existed there or whether it exists there now. The first one is Mars. Mars is in a region we call the habitable zone. This is where liquid water in vapor form and in ice form could possibly exist on the surface of Mars. And water is such a critical element. So we've been following the water. The next place turns out to be Europa. Europa is a small moon. Actually, it's not that small. It's as big as our moon. But in the Jovian system, the Jupiter's gravity and the tug by the other satellites have allowed this moon to be heated on the inside. It has melted the ice that exists in the interior, and it has created an under-crust liquid ocean with more water on Europa than there is on the planet Earth. But we shouldn't leave out another object, Titan. The more we learn about Titan, the more excited we are because it looks like an early Earth. It has the right chemical composition, It's actually bigger than our own planet Mercury, so it's a fairly hefty body with a very extensive atmosphere, and it is the only object other than the Earth that has liquid on the surface. It has liquid methane and ethane lakes. More than 200 of them we've counted already. And so if life exists on Titan, it may be very different from our own. So we actually have many different places to go and search and look at. And the signs are incredible that we will find something very exciting in the next several years. Now, why is that important to us? Well, this planet, the more we learn about it, the more we recognize that it is evolving. The climate on this planet is changing, although this actually is not a surprise if you look back in the history of the Earth. The climate has changed all during that time period. You remember I mentioned early Titan, and Titan has these methane and ethane atmospheres, etc., not dominated by oxygen at all, and yet the Earth looked like that at one time. In fact, life sprung up on Earth about 3.8 billion years ago, and it's changed everything. But when we look at the other planets, why hasn't complex life evolved on them? Obviously it hasn't, but maybe more simple life has. So by going out into our solar system, we're really opening up the possibilities of how this Earth evolves and what our place is in this solar system.
You mentioned planetary science. What is the role of NASA's Planetary Science Division?
Well, what we do in planetary science is really tackle some fundamental questions. One of the big ones that we want to know about is what is the origin and evolution of our solar system? How did the planets come to be? Why is there life here on Earth? What are those conditions that allow life to live? In addition to that, we want to look for other environments that may be habitable. Perhaps in the past, maybe there was past life in other worlds, other bodies in our solar system, or perhaps they're habitable enough for which humans, as they leave low Earth orbit, could actually move to, such as Mars. So discoveries are occurring every day in this new field because we're going out and finding them.
You're watching NASA 360. Stick around, we'll be right back. Okay, since the late 1950s, there's been a boom in knowledge about what lies out past Earth's horizon. Numerous missions have journeyed off of our planet to explore our neighboring planetary bodies.
All of these missions have broadened our knowledge considerably, but there is still so much more to be learned. Today, there are many new missions being developed that will continue to help us understand our universe and increase our knowledge even more. One of these missions, called Juno, will conduct an in-depth study of Jupiter. To find out about the mission, Johnny met up with Dr. Scott Bolton at the Lockheed Martin High Bay facility outside of Denver, Colorado. Because the craft is being assembled in a clean room, they both had to go through a little extra scrubbing before they could start the interview.
Well, right behind me is the Juno spacecraft. Juno's the next mission to go to Jupiter. We launch in August of 2011. And Juno's a really large spacecraft, partly because it's just solar powered, and we're going all the way out to Jupiter, so that's like 25 times less light than we have here at Earth. So we got 3 giant solar arrays. You don't see them attached right now, but they'll be on there. They're about 8.5 meters long a piece. So you got a pretty big spacecraft. It'll be spinning, sort of like a cartwheel as it goes by Jupiter. And what Juno's really going after is trying to understand how Jupiter formed, how all the planets formed in our solar system. And so we have special instrumentation that looks inside the planet to see how it's structured inside, what it's composed of, what the ingredients are that are inside Jupiter, so we can kind of figure out what the recipe is that makes planets. Some time ago, during the 90s, the mid-90s, NASA sent a Galileo spacecraft with a probe that went into Jupiter, and we wanted to measure the elemental composition of something called the heavy elements. We kind of knew that Jupiter was mostly hydrogen and helium, and that's like the sun. But it had a smidgen more of the cosmological heavy elements, everything heavier than helium. With that one measurement, every theory that we had on how the planets got formed went out the window. The key measurement that was missing from the Galileo probe was water, the oxygen abundance, the third most abundant element in the universe. You got hydrogen, helium, then oxygen. So water is fundamental, not just to life like on the Earth, but it's fundamental in the universe. Juno, that spacecraft behind me, has got these large radiometers, big antennas. They're square, kind of sitting on the sides of the spacecraft. Those things are designed to be able to pick out how much water is in Jupiter. Okay, that coupled with some other measurements, the magnetic field, the gravity, will tell us how it's structured inside, how much water is in there, so we can get an idea of what the recipe was that built the planet, when it formed, how it formed, what was different, what happened to the solar system after the sun formed that made Jupiter and the rest of the planets different, and especially with this enrichment of these heavy elements. And those heavy elements are important to us, not just because, we know about them in carbon and nitrogen, but it's actually what we're made of. And so we're trying to track the stuff that eventually made Earth and all of us. And we're trying to figure out, okay, what was its state early in the solar system? So Juno's equipped to go out there and get all that, and it's a really interesting spacecraft that you can see behind me.
When is this project going up?
Well, we launch in August of 2011. Okay. We first go around the sun, and we come back and encounter the Earth 2 years later for a gravity assist. So when we come back, we slingshot by the Earth really fast. The Earth's gravity pulls us and slings us out toward Jupiter, so the next pass we can reach all the way out to Jupiter. And that takes another 3 years, so we arrived 5 years after the launch in 2016.
Somebody out there was telling me that once it's out there, it actually uses very little power. Isn't that like four light bulbs worth? Is this true?
That's right. It's a very energy efficient spacecraft. It's designed that way. And partly because just doing solar power out at Jupiter is a big challenge. I mean, we've got giant solar arrays. We produce a huge amount of power here at the Earth, but out at Jupiter, we're producing a lot less. So we had to advance solar cell technology a little bit in order to be able to go out to something that cold and that low a light. Plus, there's a lot of radiation, so we got to have special protection for the solar cells. But the other side of the coin is we've made an incredibly energy efficient spacecraft as well.
What's special about this spacecraft?
So there's a number of things that are special. Besides the fact that it's solar powered, which is also unique out at Jupiter, we go right into Jupiter's radiation belts. Seriously populated with relativistic electrons, buzzing around near the speed of light that zap electronics and just cook them. We have what's called an electronics or a radiation vault. It's an armored tank, basically, and it's right there in the middle of the spacecraft. Inside of there is all the sensitive electronics. And then there's protected cables coming out of that vault that go out to the sensors all over the spacecraft. So it's very unique. It's the first time that I know of that NASA's tried something like this, and it's a very advanced concept. And Juno's, part of a long history of missions, and is part of NASA's overall program to really understand the solar system and understand where we came from and where the planets, where they originated and what's happening to the Earth. And so we go back, the original first missions out to Jupiter were Pioneer, and then you had Voyager and a couple other flybys, Ulysses and Cassini went by. And then you had Galileo, and we're really following on the questions that left. Galileo helped us focus those questions about where did Jupiter come from, what were the key questions. Now we're into the narrow science objectives that we need to get to answer these questions. What's inside of Jupiter, basically? We've got special tailored scientific instruments and a special spacecraft and a special orbit to just go right in and get these narrow science objectives that are going to help us figure out, okay, what happened? How did the first planet get made? And undoubtedly, when Juno goes there and we finally get these answers that we're after, it's going to refine our knowledge as well. And then we'll have even more advanced questions, and the next mission will come after that to go answer those. And so each mission is going to help us advance our knowledge. It's going to help us get more refined questions, and slowly we're going to figure out where we came from, what's going on in this solar system.
Scott, well, we wish you great success on the mission. We hope to see you again, brother. Huh?
It's been a real pleasure.
Another important mission being developed at the Lockheed Martin High Bay is called the Gravity Recovery and Interior Laboratory, or GRAIL.
This mission will fly twin spacecraft in tandem around the moon to precisely measure and map variations in the moon's gravitational field. Although we already have good information about the moon, there is a need to determine the structure of the lunar interior from crust to core and to advance the understanding of the thermal evolution of the moon. Here is GRAIL's principal investigator, Dr. Maria Zuber, to tell us more.
Well, the moon is our nearest neighbor in the solar system. And the way that I like to think about it is to think of the moon like you would think of a friend or a neighbor. When you think about the people who mean the most to you, it's not what they're like on the outside. It's what's in the inside of them that makes them special. And we've sent a lot of missions. We've landed people on the moon. We've orbited spacecraft around the moon. But the part of lunar understanding that we don't yet have is what's inside the moon. So to really understand the moon and understand what makes it special, we need to study what's inside.
GRAIL has a secondary mission too, which is to help us reduce risk to future lunar robotic or human science and exploration missions to the moon by providing a high-resolution global gravity field that will eliminate gravity uncertainties for precision lunar navigation and landings. Of course, all of the knowledge acquired about the moon from GRAIL will also be used to understand the broader evolutionary histories of the rocky planets in the inner solar system, including Earth, Venus, Mars, and Mercury. So our little moon is quite important for us to understand the broader solar system. Another of the important missions NASA is planning is the Mars Science Laboratory, or MSL. This golf cart-sized rover will be over 5 times as heavy as NASA's previous Mars exploration rovers, while also carrying over 10 times the weight of scientific instruments. Its primary mission is to help us determine if life ever arose on Mars, to characterize its climate and geology, and to prepare for human exploration. Named Curiosity, this rover is scheduled to work for at least 1 Martian year, or about 686 Earth days, and has been designed to explore a much greater range than any previous Mars rover. Here is aerospace engineer Jessica Collinson to tell us a little more about the MSL.
We are tasked with getting a vehicle that can, in this case, drive around Mars and meet all of those different objectives. Since we aren't sending people to Mars right now, we need to design our spacecraft to represent what a human would do on Mars. So we need to think about visuals. How are we going to decide where we're going to go? We need to be mobile. We need to have a mobility system to be able to drive around. So we have these cameras that we're able to span out across the horizon, pick our next target. We have an autonomous navigation system which allows us to drive with no instructions throughout the day. We just pick that target, drive off to that area. You need to figure out how to communicate back to Earth, so we have an antenna. And then you need to think about, well, what's the science that you're doing? And so, just like a geologist in their tool belt has all these different types of instruments, we pack them on our robotic arm on our rover. Our robotic arm for the rover has 4 elements on it. We have the rock abrasion tool that actually goes up and scrapes off the dirt that has been collecting, or the dust that has been collecting on these rocks. We have a microscopic imager that will allow us to zoom in closely and take a look at what the actual structure of what these elements look like. And then we have 2 science instruments which help us determine what actually we're looking at and what the mineral makeup is. It's our own little personal field geologist out roving around Mars telling us all about what the Martian soil looks like.
We'll be right back. You're watching NASA 360.
Other than Earth, the most studied planet in our solar system is Mars.
Although we know quite a bit about Mars, there are still some lingering mysteries, like why is its atmosphere so thin? At one time, Mars had a dense atmosphere that supported the presence of liquid water on the surface. But due to dramatic climate change, most of its atmosphere was lost.
To help unravel this mystery, a new mission called MAVEN is headed to Mars. MAVEN is designed to make definitive scientific measurements of present-day atmospheric laws that will offer clues about the planet's history. Johnny spoke to MAVEN's principal investigator, Dr. Bruce Jakosky, at the University of Colorado to find out more.
We've been doing Mars missions for over 40 years. This one in back of me is one that was in the late 1960s, and we're really excited to be continuing that with the MAVEN mission, which launches in 2013. MAVEN stands for the Mars Atmosphere and Volatile Evolution Mission. It's an orbiting spacecraft that is designed to understand the history of the Mars atmosphere. Why is that an interesting question? The spacecraft we've sent over the last 40 years have given us a lot of information about Mars. They've provided convincing evidence that the climate on early Mars was very different from what it is today. The atmosphere was much thicker, temperatures were much warmer, there was liquid water. So where did all the CO2 go? Where did all the water go? One of the possibilities is they all went down into the subsurface, but we're exploring the possibility that all that gas, all that water was lost to space. To get to space from the atmosphere, it has to go through the upper atmosphere. So we're going to be looking at the upper atmosphere of Mars, the processes that control the ability of gases to go through it and how it's lost to space. The goal of the mission then is to understand how much gas has been lost to space through time. The questions that MAVEN is going to address really get at issues like planetary habitability. How is Mars able to support life? To what extent was it able to support microbes early in history and not today? And it really gets at this question of, does Mars have life? If it does, how is it supported? It's something that excites people. It's really the driver in many ways of why we're exploring space, exploring the planets and out beyond our own solar system to understand something about the history of life.
Understanding the Martian atmosphere, will that help us better understand Earth's atmosphere?
It will, but that's not the reason we're doing it. There's a couple of issues in here. By understanding the Mars atmosphere, we understand many of the same processes that operate at the Earth, but in a different environment. So we're looking at different boundary conditions. It allows us to better understand the processes. But the most important issue is that Mars today doesn't have a magnetic field, and that means that the solar wind hits the atmosphere and can strip it away directly. It's easier to lose the Martian atmosphere. The Earth has a magnetic field, and that causes the solar wind to stand off, and it protects the Earth's atmosphere. If we want to understand the Earth's atmosphere, we really do it by studying the Earth's atmosphere. I think the reason we're studying the Mars atmosphere is not just to bring it back to Earth, but it's really to understand the Mars atmosphere, to understand the nature of planets elsewhere in our solar system. What's the range of different types of planets that might be able to support life? So by studying Mars and the other planets in our solar system, and now the other planets outside our solar system, we really get a handle at these broad questions of the nature of planets, the nature of life and how it interacts with planets, and the distribution of life within our universe. So we're really excited about this mission. We think it addresses really important science questions about Mars that have broader applicability, and we think we've put together a first-rate mission that can move forward and get us the answers to these questions.
It's fantastic. Bruce, thank you so much for your time, and we hope to see you again.
Thank you. I
Definitely.
appreciate the opportunity.
Our pleasure.
So today we have learned just a little bit about some of the missions funded by the Planetary Science Division at NASA. But trust me on this one, it's just the tip of the iceberg. In the coming years, new discoveries and adventures will unveil themselves to us. And thanks to NASA, we'll have a front row seat. For Johnny Alonso, I'm Jennifer Pulley. Catch you next time on NASA 360. Number one. Sorry.
And I'm Johnny Alonso, and today on NASA 360, we're going to take a look at why and how we're doing it in today's modern age. Modern age. Owen got it.
And if so, where will we go? Yeah, hey, get, go, go. Trying to get my paper. But even with the wealth of information we've learned from our numerous space missions, there's one major question.